Hi, I'm Darren McHugh and I'm going to give a presentation today on particle shape applications. This was done using a direct imaging non-product contact particle size and shape technology, the Eyecon2. This would be a good presentation if you're interested in learning more about shape parameters, what to consider when measuring your bulk solids, different applications that this can be applied to find out more information about your product so you can make better decisions about improving yield, reducing content uniformity, and overall improving efficiencies across your processes. So let's jump right in. So I'm the Senior Product Manager for the Eyecon2. That's our direct imaging particle size and shape analyzer. It's been on the market for over 10 years. It's really used where bulk powders flow to measure inline in an automated fashion to get your data to make decisions about improving quality, for example. I also look after our SmartX platform, which is our vertically integrated manufacturing platform, which is really a automation and digitization platform where you can take in third-party sensors like PATs, NIR technology, PLCs, communicate with them, and any digital technology really, and bring it all together to connect it so you can read all the data for one thing, as part of a data historian, but also control the processes together. So maybe changing things like the flow rate on a piece of machinery based on its particle size from a PAT or moisture content. It's been designed for process scientists, so it's designed to give them the ability to do the automations in a low-code, no-code fashion. So to assist with digital transformation journey of moving from paper to glass. If you'd like to learn more on that though, reach out. That's what we're here today to talk about in detail. We're going to be talking about particle shape, and so sieve analysis is really the most traditional form for determining particle size. It's robust, it's cost effective. Every analytical lab really has a set of sieves, but it's not without its drawbacks, of course, for shape, especially because it doesn't determine shape based on a square aperture for what material can fall through it. In this example, you can see an elongated particle can easily fall through. So it's more of a volume based method and has a certain amount of resolution because you can only stack your sieves so high. So this is like one of the base methods out there for determining particle size. But if we look to more digital technologies, mentioned here is dynamic light scattering, laser diffraction. The last two, dynamic image analysis and static image analysis, is what the Eyecon2 is, being an optical based method. And that's really the only methods that offer the ability to measure shape, because you can take 2D images of your particles and attribute those qualities to shape profiles, whereas the other methods are using media scattering or Brownian motion or basically laser diffraction to determine the size, but not the actual shape of your particles. But what's important from this slide is just to note that there's various methods out there to measure size and shape, but it's not one size fits all. It's really dependent on your application, and we'll get a bit more in depth about that when we talk in more detail about shape applications and all the different factors that are out there. Here we see the specifications for the Eyecon2, but it's essential to say it's an industrially designed rugged device suitable for at-line and in-line measuring of particles and bulk solids within these size ranges. If you'd like to learn more, of course, please go online and see some of our content there. Here's an overview video that you can watch to learn about basically the differences between the dynamic image analysis and static image analysis applications for these technologies. It's really used from the start to the end of any manufacturing process where bulk powders and their size and shape are of interest. So right from dispensing at the raw material side of the factory, where it goes through its unit operations to when it reaches its final product of either packaging or in this case compression, you can measure particle size and shape inline to help improve each one of those processes from process to process. So if we look at the data that you get from this type of technology, we're looking at the EyePASS software. This is the image analysis software that's used on the Eyecon2. The red box is showing that you're getting a full particle size distribution, and then toward the end of that right box, all those areas of eccentricity and circularity and elongation are the shape measurements that I'll get into in a moment. But because this is a nice comma separated value file, a CSV file, you can really work with the data. You can put out charts and tables that you want to investigate and start to learn more about your products and processes to improve things like yield based on shape. And then there's a formatted PDF report that can be output by the system as well. So why is shape so important? Why should we care versus maybe just measuring particle size? Well, the most common reason is manufacturability, and that then comes down to flow is one of the most common reasons maybe someone would be interested in shape, but it's not the only. The applications we're going to show today will really kind of drive that home. But if you, let's say, take the two examples of sugar and flour. So let's say you're trying to dose two things with those. You're trying to dose your coffee in the morning with a spoonful of sugar. The sugar will typically flow off the spoon quite easily, as we all know. There's not usually anything left behind unless the spoon was wet. And then flour is another good example where you're trying to dose the correct amount into baking a cake. And as we all know, sometimes when you open the bag and you go to pour it, it'll come out like an avalanche and you'll overdose your cake. So it's two good examples of where the powder flow can really affect the manufacturability of your end product. It's not the only two, but it's the base kind of level. And the metric that's used to measure this kind of flowability often is the angular repose. So how the particles flow over each other. On the right here, we see a few different flow patterns that are undesirable. You can have things that happen such as rat holding, where only the material in the middle will fall out through the orifice of moving material from one process to another. Or you could suffer things like, segregation. You want an even product content uniformity. And if that's not happening, you might be leaving some of the desired material behind and not getting the right dosage at the end. And tablet manufacturer would be a good example of that, that undesired effect. But then there's, of course, cases where you do want irregular shaped particles or particles of different shapes. Good example of that would be, railway ballast, the stones that you'd see at the bottom of a railway line. They're of a certain shape so they can actually interlock to each other mechanically. And that's so that a train driving over them at speed will not pull the stones up and out of their bed that's holding the railway tracks down. So there's something that we take for granted, thinking that those stones are just random. They're not. They're of a certain shape profile that's been chosen for that job. The same goes for filtration methods, using a carbon filter under your sink that's filled with activated carbon. And that has a high surface area with lots of nooks and crannies for the water to flow through that material so it can absorb all the contaminants in your water, as an example. And then if we go further into some other applications, the 3D printing is where you have a really, where you want a really high control on the sphericity or how circular your particles are to make sure that the real good content uniformity. So in the space of 3D metal printing for aerospace, for example, or even aeronautical, you want to make sure it's all uniform, because if there is a contaminant in there, if there's an irregular shaped particle, and when you go to laser synthesize it all together and it's not all binding together in the same way, that can be a stress point. Maybe where tensile stresses are applied, it might start to crack and fissure at that point. So hence, for things like rocket engines, which are more and more 3D printed these days, the control of the raw material shape is a huge factor in that industry. So there is more than one shape parameter, much the same as there's one more technology to measure size, and there's more than one way to measure size as well. The EyePASS software can report back these variables here: eccentricity, aspect ratio, circularity, and sphericity. There's a few more on the next page. Which one to choose will depend on your application, which we'll kind of give examples of to help you decide. But the benefit of automated image analysis is that you don't have to choose at the time of measuring. You have all this data recorded in your CSV files. It's just up to you to go analyze and see what the data is telling you about the shape of your product and how it's affecting your process. And the other shape profiles we can report are elongation, convexity, and compactness. And the formulas are given for those here really as well. So, elongation, a width by height measurement showing how elongated the particle can be outside of a square. Convexity is an interesting one as well, because if you get the boundary of the particle and were to apply something like a rubber band to it, this will tell you like the, again, like the nooks and crannies of that particle, the overall shape profile of what it is. And then compactness, which is like the area over perimeter, it'll give you like the actual compact shape of the whole particle. So there are all the different shape parameters we can report, but which one should I use? What one actually matters? So we're going to give like an example of 4 case studies done here, 4 applications where customers have come to us to measure the shape of their product. And let's see what we can infer from the data. So we have the 4 samples that were sent to us. We have an activated carbon, which is the water filter. That is the material with all these nooks and crannies so water can pass through it and capture all the contaminants. A very dark black material. We have the chopped extruded rod. So this comes from an extrusion process where basically a rod comes out of a machine and is equally chopped up into pellets, essentially, that are then later used for processing via hot rolling vinyl floors. So control of that product would avoid things like voids in your floors, in the roll. There's the aluminium oxide, a very abrasive material, sharp material, which is desired for obviously cutting discs, grinding discs, polishing wheels. And then the sugar crystals that are also, want high flowability from them as well. Unfortunately, the customer in this case did not send us the cake, as seen in the picture, but maybe next time. The middle image is interesting because it's the subsampling, and that's always good practice, regardless of particle size and shape, following the ISO standards for good subsampling practice, where you're taking maybe something from a process of 1 kg could be the batch. And for the at-line for the Eyecon2, you need to get it down to about 5 grams. So you have to practice good subsampling using even an automated subsampler. In this case, we used a riffler, which is a chute that evenly divides the material. So you can take it from 1 kg to half a kg to a quarter of a kg and all the way down to 5 grams. And that's just good practice. That's desired when you're doing subsampling, especially if you're using it for at-line, putting material underneath the camera, let's say. Not so critical if you're measuring in the process where it's actually being manufactured. And on the right is showing that a pseudo rig with a vibratory feeder we developed just to test larger sets of materials in a mock inline setting. Whereas ideally you would mount this Eyecon2 technology onto the process making the product. So here's just a little video really showing that in action. Material passes by the camera system. It constantly grabs photo, illuminates it from front illumination of red, green, and blue LEDs. There's the images being captured, and then there's a glimpse of real-time data coming across on the software. There's different configurations that it can be installed in. We always try to go for the inline process right where it's being made, which makes the most sense for making decisions about changing the process to improve the product quality. But it can also be changed to these other methods such as on the line or at the line and of course off the line. So let's look at these 4 samples a bit more detailed. So we have the activated carbon. Let's start at the top. On the left was the at-line sample presented on a tray. It's just photographed with a phone. And in the middle images here are the raw images taken from the Eyecon2. And then the colorful images on the right of that with all the different colors is the masking, basically the image analysis, determining what is the edge of these particles so it can apply all the different methods for measuring size and shape. We can see the extruded vinyl rod. Similar to raw image. This one was interesting because if you can see in that middle image, because it was an extruded rod, which is circular, cylindrical, and it's chopped, and it's chopped at such a degree that depending on what way the rod was facing the camera, like it looked like a circle or a square, but was successfully matched for the particle size and shape of both of those. And then we've shown in a bit more detail here the white aluminum oxide and all the various measurements and sizes that we can apply to it via image analysis. Again, all automated, so we're getting all this data at the end that we can analyze. Lastly is the sugar crystals, which is interesting because just from the images you can tell there's quite a large population size and shape happening in that area. So if we were to characterize these a bit further, just to show it here visually before we actually apply anything like say for metrics or for data, is that the activated carbon is quite a jagged material with lots of nooks and crannies. Extruded rod, depending on what way you look at it, it'll look quite circular or square. The white aluminum oxide is quite sharp and abrasive material as we expect. Each one of these particles in the images essentially got at least 1 if not 2 sharp edges on it at the end. And then the sugar crystals, which are quite large in distribution but fairly uniform in shape profile overall. So we have all that analyzed, we have all the data. EyePASS version 3 of the software, which is using machine learning image analysis, has the ability to measure all these particles per particle in the image. And that's what we're seeing here in these CSV files. Each row is a per particle data. What we're interested in today is in the orange here on the right hand side, where we're showing all the different shape parameters and how they're determined. So we've got all this data. Let's what do we do next to actually investigate it a bit further to see what effect the different shapes can have on the product. So here we go back to a traditional method called the Krumbein scale. This came out by William Krumbein back in 1963, who was the first person to ever actually try and categorize and classify shape against a kind of metric method. So what you do is you take a population of particles. You would take 20 particles out of that whole population and compare them on a scale of sphericity versus roundness, a 5 by 4 comparison. If you look at the image here of the chart, you can see in the top right is the 0.9 most spherical kind of particles that you have, and then in the bottom left is the most elongated particles. So this is like the traditional method that was first done to categorize particles by shape. It's quite a small sample, only using 20 particles based on whatever size population it could be, tens of billions of particles. So there could be a few arbitrary things to infer from this. But thankfully we live in a digital age and we have all that data from the CSV file. So we can instantly just compare sphericity against roundness. Looking at the activated carbon here, with the raw image on the left and the segregated image on the right, you can see it's an interesting enough population where it's pretty spherical and round, because most of the population is somewhere between 0.8 and 0.95. A couple of outliers, of course, for elongated particles or maybe even possibly contaminants being picked up in the images. But overall, you could say for this material that has lots of nooks and crannies in it, it's not very spherical. I'm sorry, it is very spherical and it is very round. It's not very jagged, it's not very pointed or elongated overall. So that's an interesting area to look at for that. Like, it probably flows pretty well, which is what you'd want, especially if you have a filter cartridge where you want the water to pass by it. You don't want this material to interlock into itself, clogging up and blocking a water filter, for example. So if you start to see your activated carbon was going more toward maybe the 0.5 region of both sphericity and roundness, and you're noticing your filters are clogging sooner than they should be, that could be an area of concern for that. The chopped vinyl rod, where it was depending on what way it was orientated to the camera, you'll be looking at a circle or a square. This was quite interesting because of the segregated populations. So we can actually identify which ones were circles and squares based on these two comparisons. So that's what was interesting. What might happen in this case as well, if you were suffering more contaminants, maybe like elongated particles, like this red one that made it into the process somehow, you would probably see those a deviation or a drift from these two standard values of sphericity and roundness for those two shape profiles that you have within the same image area. So that's interesting. Looking at the aluminum oxide, this was actually a wider, let's say, profile of roundness and sphericity for ranging from mostly 0.7 to 0.95 again. So, not as uniform as the water filter, for example. And that makes sense when you look at the image, because we've got sharp particles in this image. If not one edge, it's usually two edges, and each one of these particles has a point, meaning that they shouldn't really be coming in as very spherical overall. And that's what we're seeing here. And then finally, actually, the sugar crystals, which was a very wide distribution between size and shape. We had a lot going on in that image of those different crystals. And again, that's showing here as well that there is a huge population of round and spherical particles in there. Not very high-end roundness or sphericity happening in that population, which is interesting because sugar does flow very well. So that's just an example of taking 4 different materials for totally different applications and what shape could actually mean for those applications. The great thing is it's automated image analysis. We're using these outline samples where a minimum of at least 900 particles versus the 20 of traditional methods. So you get a lot more data. It's more statistically relevant. If you were to use it inline, these data points could be up in the tens of thousands, if not a million data points, because you're continuously measuring your process. And that's the benefit of digital inline technology. So really to sum up, I should say, the presentation today is really just to give an idea of what this technology can do, that it's automated, it's digital. You can do quick comparisons like that to infer more from your data to make decisions about, quality control of your products and processes. And shape, like I said before, is often like a hidden metric that a lot of people overlook. But with the benefit of it being built into the size and shape technology of image analysis, it's something people should take a closer look at. Pun intended, I guess there. So that's really it from me, just to show that this is suitable technology really for measuring size and shape. If you have any questions or want to learn more, please feel free to reach out to us at InnoGlobal. Thank you. Have a good day.